I will discuss some results about function fields and related to also Drinfeld modules. So, I mean, Drinfeld introduced first Drinfeld modules and the moduli that led to celebrated achievements in the Langlands program. But if you focus on one Drinfeld module, you can actually study its arithmetic properties. And I will study a particular Drinfeld module, which is the Carlitz module, and one of the simplest one. And so, name Carlitz comes from an American mathematician, Leonard Carlitz. He introduced the Carlitz module, in fact, in the 30s. But it was not known to Drinfeld because Carlitz used to give weird names to his paper. Let's say it was not really obvious what it was, and also he published like something like 800 of papers. So it was very fun, I guess. Focus on the way. But okay. So let me introduce the Carlitz module, but before that, some notation. So here, F will be a finite field with Q elements, and A will be the ring of polynomials over F. So the Carlitz module is the counterpart of GM in a function field. So GM is a functor that takes a ring, so a Z algebra, and lands into Z module. So this is the same thing here. So, but with Z replaced with A. So I take an FT algebra, and I land into FT module. So I will first change the name of the variables, since those two are going to be joined in the same ring soon after. And it works as follows. So in the rule that take an FT algebra and associate to it an FT module. So as an F vector space that just R with the addition, so as a F vector space. And there is an action Ft, which is given as follows. So for any x in R, T will act as So it seems relatively different to GM, but it has it shares similar properties. For instance, so let's say first C, it's a FT module scheme, which is smooth and connected. So if you replace accordingly the polynomial's occurrence by Z, then it's the same as GM. And also C is of rank 1. So meaning that so if I take let's say L of T or L of T, a monic irreducible polynomial, i.e. a prime. Then I can look at the C torsion of at the L torsion of C, or let's say FT plus F, and this is a real rank 1 over right. And if you replace accordingly polynomial of occurrence by Z, then actually the two conditions will characterize the forms of GM. And if you add other conditions that are natural, let's say, then you can actually describe C and GM. And that's, I mean, I'm not going to talk about this, but you can have a look at the work I did with Junga. So it's in French, but it's a PhD student who actually used ChatGPT to translate it in English. So you can have your own guess on the subject. All right. Okay. So there are many things in common with GM. Let me introduce the basic ingredients. So there is an exponential function. So let's say there is a. So let me introduce more notation. So K will be the fraction field of A. And so just lt, and I can take the infinite place, which is the only one not seen by this ring, to the infinite place, and I can complete this thing. And then you can take a separable closure of it. Right? And there's an exponential map that goes from infinity s to also k infinity s, but now seen as an FT module with the Carlitz action. And it's objective, and there is actually a kernel, which is free of rank 1 over theta, which is generated by the so-called Carlitz packet. So we give a formula for that. And so you can already see where this statement comes from if you act by, so this is an exact sequence of FT modules. So if you act by L on here, then this is multiplication by A theta here, also as well here, and then you just act by LT. So the LT torsion is in the kernel of that, and then let's say snake lemma, this is just isomorphic to this one. And so the exponential has a nice formula. I mean, it's analytic, and you can actually write it as a Fourier series, where so let's say d0 is 1, and d1 is ft minus theta, and then sorry. X.
They're super able to see at X.
Thanks. All right, X is an element in infinity, yes. And all right, etc. So, I mean, this is a Q to the I. Yeah, you want it to be an additive map because it's a sequence of FT module. And so Carlitz introduced this function, and I already realized that this is close to be a counterpart of the factorial of an integer. Instead, that you only define the factorial for powers of Q to the I. So he defined what is now called the Carlitz factorial. So he extends the definition. So it's di with di with the ci at the q digits of n. So and there's also now a counterpart of the Bernoulli number. So this is the factorial. And there is a counterpart of the Bernoulli numbers. How do you do that? You just define Bernoulli Carlitz number as by the following power series. Yeah. So there is no the shift by 1 because now 0 is 0. Those are defined. So they're actually in all right. There is also a local inverse of the exponential, which is the Carlitz logarithm. Oh, everything is called Carlitz. Again, on this form, where now I integrate 1, and 1 is theta minus theta q. And you can go on like this, and it's a Carlitz logarithm, and it converges now for degree of x smaller than Q over Q minus. And similarly, you can define the n's Carlitz polylogarithm just by taking the denominator to the power n. So,
I'm going to come to in the definition of the infinity. Do you want to use t or zeta?
all right. So I should. So it depends on the role of k infinity. In this situation, it's theta. Yes, I should have written it. But so the variable t will appear whenever it's used as the coefficients, and for the base field, it will be theta. So
T is theta.
Yeah. I think I will also use k infinity for the completion of the ring of coefficients. So t might appear as well. All right. But you indeed, yeah, it's coefficient. All right, and then the nth polylogarithm is just defined in that way. And since this converges for degree of x modulo n q over q minus 1, then this thing converges in a slightly bigger radius, so converges for degree of x over n q over q minus 1. All right, and I'm almost done. I want to introduce Carlitz zeta values. So now n is an integer that is bigger than 1. And the Carlitz zeta value at n is defined as the sum of harmonic polynomials. Now it's a t. So it's really what you would like to consider. So it converges in k infinity t. But let me write it in another way. First, I take the sum over the degree, and then just over the monic elements with the degree of a being. So using this expression, David Gross realized that actually when n is negative, then for d big enough, depending on n, then all those sums are 0. So you can actually define this zeta value for negative values of n. Although there is no known functional equation for this expression, you can still define negative values.
So, okay, I'm confused by the t's and thetas again. So this is a t or a theta?
So now it's a t because it's a t because zeta values are I mean, you can replace by theta if you want for now, but it just means that philosophically the t that appears here, this is belongs to the coefficient.
What is k infinity? Is it 1 over theta or 1 over t?
So it's so depending on the situation, if you are looking at the coefficients, this would be a t. If the thing lives over somehow the base field, this would be a theta. So here the zeta values are constructed using determinants of stuff that live in the coefficient, so they will appear in the variable t. But if it confuses you, you can just take this expression without it.
Okay. And k infinity, is it like a completion of k? Like
it's exactly the completion of k at the place being the degree.
Okay. Why did we go from t to theta? Like there, here.
Yeah.
Is it also a theta and that's also a theta? The
a. Okay. For now, I mean, maybe the things we get clearer. Imagine that everything is a theta.
Okay. Everything.
And then we get clearer maybe after. Okay. Sorry. I mean, I'm using the classical notation in the literature, but maybe this will get clearer when I will introduce t-motivic. All right, so maybe something that troubles me a lot is that I mean, we learned from the work of Borel, Lichtenbaum, Deligne, Benison that zeta values are expressed in terms of K groups, volumes of K groups, and then there is no known, let's say, counterpart of K theory in the function field setting. Let's say K theory giving rise to FT modules. I mean, there are definitions of K theory that just solely depend on GM. And, I was wondering whether you can just replace formally GM by the Carlitz module, but I don't know whether it works. So another way to construct K theory is just, another way K theory appears is that motivic extensions of Tate twist, and this is what I want to study the counterpart of that in that situation. So let me first introduce maybe t-motivics.
Yeah, sorry, I tried to go replace all the t's by thetas, and then I got confused by this definition of the C.
So exactly, I mean, so C is an FT module, but it's an FT module scheme living over F theta, which means that theta is the variable on the base ring, but it acts on the module scheme of T.
Can we just replace the t's by thetas with where they should be replaced in this board? Like an A is theta, right?
Sorry, where?
Wherever it should be replaced. Can we just do that replacement now?
Like up here, maybe everyone is unhappy about the definition of K at the top. Should that T be a theta?
Here, yeah.
But then A itself.
Oh, not there, yeah.
Then it's not a name of the scheme. Okay. Sorry for that. Yes. Yeah, sorry. I mean, in a minute that would be. So, I mean, I hope. So there is a definition that goes back to Anderson in 86. So a t-motive over, let's say, I will just consider things over F theta. That is data. So first, M is a free module. Now you see that the two variables are in the ring. Maybe I should start with that. And on this ring F theta, so there is one operation that is the Frobenius, which is still linear, but acts on theta to the power 3. Right, and so the second point is just the data of an isomorphism from the. So it's a tau linear isomorphism with poles along t minus theta. And this is actually why I was confused previously, because all those series will actually appear when you specialize at t equals theta. I mean, near the where arch theory is. So actually, this truth replaces here t by theta roughly, but not for the zeta. So let me give some example first of what is this. So the one of the easiest is what we call A-1, which is the realization of the Carlitz module. What is this? It's just defined as the homomorphism between P and GA, seen as homomorphism of F Q vector space scheme over F theta. So here you see that you have on the left you have an action of ft acting on C as an ft module scheme, and on the right you have an action of the isomorphism of GA. Space scheme over theta. And since it's reduced, let's say twin the ring in a theta with the probability of GA. So in particular, it's an f theta t module with a particular action of the Frobenius. And so the Frobenius is actually here. So in fact, this is how you get the pole at main theta. So let me write it mostly most of the way. This is just the free object of rank 1. Well, the Frobenius is just the semi-linear multiplication by 2 minus 2. Then you just mentioned that you can order then A1 is defined as the dual of the A minus 1. And then AN is the nth tensor power of A1. Right. So if you are familiar with prismatic cohomology or BKF module, this is actually remarkably similar to the notion of BKF modules. So a remark. A BKF module is just the data of a main module. Let's say with you can add some condition, regular condition, like say projective or so AINF is just the typical bit vector, let's say over OCB, that, and then there is a Frobenius on this string, and it is also the data of a semi-linear homomorphism, which is invertible once you invert psi. Psi is a particular element which generates the kind of the Fontaine's map theta. So here the counterpart of the Fontaine map would be just let's say the multiplication map from so it's also an happy coincidence that Anderson already defines theta as the image of T in here. Yes, thank you. So they will play the role of some kind of a global version of BKF module. So, so for BKF module, you can define different realization. There is the Tate realization, for instance, where you just cancel with a bigger ring, namely the p-element vectors over CP flat. And then you just look at the invariants of the elements that are left invariant by the Frobenius. So there is Anderson already introduced a similar thing, which he considered as being the singular realization. So let's first introduce the following ring. So let's take infinity S T. Just be the Tate algebra with coefficient k infinity S. Just the equals to 0. So given a t-motive, Anderson defined the Tate realization as being the invariant of tau m once you cancel m with this figuring. So again, if we take the example of the Carlitz module, or let's say A1, if we look at the A1 Betsy, then there is it will be free of rank 1, and there is a particular element that generates it. So it's an FT module generated by omega, where omega is a particular element. So if you apply by this, I mean the Frobenius in acting on theta, so just raising the coefficients of this to the power q. So let's say this is f, and find this to be so just the extension of tau to this ring. Then it should satisfy. Oh, maybe something I want to mention. So also the notation of A1 here is inspired by the fact that if you look at what should be the A inferiorization of H2P1, then this is just A in equipped with the seminar multiplication by xi. And xi is really the kernel of theta, so this is similar to what we have here. And the notation is A in. All right. So for omega, you have a formula, the following. It's, you put the q minus 1 root of minus theta, and then take them. Following product. I mean, look at this relation and try to make it convergent. And there is an element here. I mean, if we look at what should be and those are also the invariants of the Frobenius, and dp time the elements near the mu. Right, and I said I would give a formula for pi tilde, the Carlitz period. So pi tilde, the Carlitz period is defined actually as so you first twist omega and then apply t over. So this is the Carlitz period, which was the So this is why the t equals theta did not matter previously, because here I specialized to t equals theta. All right, so as I explained, some at least part of K groups appears in extension of Q0 by Qn. So very interesting to look here in the similar situation and to study extension groups. Yeah. Maybe I should mention first that so this defines a functor from the category of t-motifs to a t-module with actually an action of a gamma group. So define functor from the category of modules over ft equipped with an action of gamma group of f. And if you wonder, I mean, this is just the counterpart of the complex conjugation acting on singularization. But the problem is that this functor is not exact, and the issue comes from the fact that this ft module might not have the same rank as the one of R, so we'll restrict to a subcategory of we did analytically trivial objects, which just means that the multiplication map so first take so let's say that just that they become trivial once you extend the ring to APTS. So this map is just so now so so if you take M and N two objects in this category, then and you consider an exact sequence. So since the underlying modules are projective, then it just means so it splits the module, and you're just giving precising the direction of the Frobenius. So in particular, in this situation, you get a map from and so
any extension automatically rational? Analytically trivial?
so yeah, whenever whenever those two are rationally trivial, it will be yeah.
this is pretty tangential, but I mean, usually when you inform, for example, such a Tate algebra, one would want the coefficient field to be complete to start with, but you work with a non-complete field.
Yeah. Yeah, I could have taken what we call C infinity, which is the completion of a K infinity S, but in this situation, I mean, for at least for original 8K trivial object, this is equivalent. In fact, the action of G infinity is continuous, and so this factors from a finite extension of a separable extension of K infinity. So maybe let me just explain the case where n is the trivial object. So by the trivial object, I just mean the rank one object, but the Frobenius is just the identity in the semi-linear multiplication by one. In which case, you just have an isomorphism. So just the isomorphism works as follows. So you're just taking an element in here and map it to the Frobenius has this form. So you just take the class of the element and you map it to the just and that's the beta where the Frobenius is just so the first remark I want to make is that this is an FT module, but because we have a pole at t minus theta, this will never be finitely generated. So this is never finitely generated. I mean, but in the case of n is 0, but and there is in number field there is a conjecture of Bayesian that's stating that the extension of motives over Z should be a finitely generated module. So we have to find complementary conditions to make at least to consider a submodule of that thing which is finitely generated. So there is two reasons why this is not finitely generated. So the first is the one I explained, that you have a pole at t minus theta which cannot be covered by what you quotient with, and so a reason for that is can be related to the fact that there is an Hodge realization functor, and that this Hodge realization functor is not exact. So maybe let me say this orally, because I don't want to spend much time on it. But so if you look at the image of tau m in M once you invert t minus theta, then you can look at the elementary divisor with respect to t minus theta, and this gives you Hodge weights, and you can make I will define. I will make the following definition. So an extension is regulated if the Hodge polygon of m plus n is equal to the Hodge polygon. And it's equivalent to requiring that the Hodge ping functor on those extensions is exact. And so now that I think of it, this might be, I mean, there might be also some Nigal filtration lurking sounds, and then that may be equivalent to this extension, so to the definition somehow. But So the name regulated really comes from the name from the notion of regulator. Regulator just is the map induced on the extension groups for taking the authorization, and you're just asking this to exist. All right. So this is a first condition, and you can define the modular regulated extension of n by m as being those sequences. There is another reason why this module is not finitely generated. I mean, so I mean by this I mean that this is still not finitely generated, and this comes from the fact that this Gara group is huge compared to the complex conjugation. So let me rather say that there is I mean, now we restricted to the category of reasonably trivial t-motives. So this functor is exact, and this induces a map on extension. So just look at regulated extension of by m, and you can use the exactness of the Betti realization. And this will land here. So the module with a continuous section of infinity s over infinity. All right. And compared to the classical situation, so for number fields, that would just be mapping certain extensions to the extension of a finitely generated module with an action of a two group. So that would be I mean, this would be a 0 to z module. But in our situation, this thing is not finitely generated at all. It can be rather huge. So let me define at least in the case n equals the trivial thing, that would be easier to state. So by our Betti this map, which is the kernel of it. So I'm just looking at extensions that are both regulated and split with an action of this given group. And I will also give a name to the co-kernel of that. So the first theorem is that both modules finitely generated. So at least for the first part of the statement, this would be the counterpart of Beilinsen's conjecture for t-motives, because both regulated is empty for number fields because the authorization functor is always exact, and yeah, I mean, as I mentioned in number field, this thing is a finite group, so saying that the kernel is finite would be the same as the module itself is finite, and secondly, so if the weight, there is nothing of weight, and if the weights are negative, which is the case where for Tate twist, so let's say the weight of this thing is minus n. If the weights are negative, then in fact, this is the portion. And the rank of this thing is equal to the dimension of a certain extension space of a Hodgkin structure. I will not define what this is, but And actually, this thing is a k-infinity vector space, but now in the variable t. So it's,
Can you just like write down like the kind of table of analogies between what you find and like number field version?
sorry, can you say again?
Can you write down like a table of analogies between what you've defined, like all these X groups in the number field version?
So you mean what would be this X rule for number fields?
Like this is meant to be some kind of motivic homology, right?
Yes, yes.
And what is the other thing, like class?
So this actually I do not know. I mean, if you think about the classical situation, so this would just be x1m going to h1 of gal c over r acting on the Betti in the singularization of m. So that would be a T. Likely the coordinate of that map will also be a 2 group. So it seems to be that the coordinates of that thing would just be a power of 2 to me. But yeah, I have no more grasp on this group. I mean, as I will explain, this actually computes the level. Maybe I have some computation after all that maybe can help to grasp on these things. So I mean, I can just state now the results there. So let's say theorem. I will show you the computation when m is an. So we have the following: regulate the extension and infinity of this thing. So classically, as I understand it, that should be at least rationally so this I expect to be related to some kind of K groups. So first of all, if n is negative, this is 0. Now for positive n, q minus 1 does not divide n, then this is actually free of rank n. And n is positive, but q minus 1 divides n, then in this case, this will be a rank n minus 1, and there will be extra ordering. So let me write epsilon n for the torsion is cyclic, generated by some polynomial epsilon n, and I can give you the formula. So epsilon n is actually t to the q to the l minus t to the power pc, where so n is divisible by q minus 1. So I write q minus 1 m. Okay, well, that is the end. So C is the evaluation of m, and L is the LCM of the R, so that's QR minus 1. Now there is a funny thing. Yeah. So basically the torsion of K groups is explained by I mean it's the computed in terms of denominators of value numbers. So it's I think the denominator is roughly Vn over n. I mean the torsion of the K group is something like the denominator of bn over n up to the power of 2 maybe. So we actually checked that if I take this thing, so it's Carlitz factorial of n minus 1 over Carlitz factorial of n, so it's roughly bn over n, and I multiply by epsilon n, then this is actually integral. So yeah, we see. I'm using coincidence. And maybe so that there is another result as well. That's so as I explained, there is so if you look at the first formula on top of the board here, so if you take M to be the Carlitz module, then we just have a map from M where you inverse the t minus theta to the extension. And let me just define first. So for alpha in f theta, with degree of alpha smaller than nq of q minus 1, then we define the polylog class of alpha. So we write it like this, and this is defined as the image of this map of just alpha t minus theta ds. So and we can check that this actually indeed belongs to so it is both regulated and splits as a representation of G infinity. So it is here. Maybe. Oh, actually, that doesn't matter. And the second theorem we have is that if I take alpha 1 up to alpha s elements of degree smaller than nq over q minus 1, then the following are equivalent. First, a certain relation among this polylog class is 0 in the extension groups, and second, that if I apply theta and I just consider classical polylogs instead, and this belongs to an integral multiple of theta. So
Last T is a theta.
maybe at some point. Thanks. So this looks like some kind of a Zagis conjecture, or I mean, but in a very simple form. But anyway, there is a result of Chang saying that whenever some Carlitz polylogarithms are linearly independent, then in fact they are algebraically independent. And we try to generalize the results to a kind of polylog. So let me just say to conclude that the following series is quite important. So if alpha is in theta, then we can consider the following series. Alpha to be the this theory converges, and you can look. It's a kind of a deformation of the classical polylog by n depend on alpha, and I can write it near the pole t minus theta where Hodge theory is happening. So if you look at when you look at the expansion at t minus theta, so you first will get a term like this. So first you get the Carlitz logarithm, and then you get some kind of higher version of those. And here. So I mentioned that there is a regulator map from extensions of t-motifs to extension of Hodge structure. And what we claim is the following. So, a regulator from certain extension space. So I have to enter with certain space of Hodge structure. So it's given by certain matrix of where here that's certain elements alpha 1 up to alpha s in f theta. And we were interested in, so Bayesian's conjecture predict that this thing should be an isomorphism in for when n is negative. And so actually, when n is a prime, let's say n is p, then this thing is actually a p power. So all these coefficients will be 0. So the matrix cannot be an isomorphism. So but whenever n does not divide p, it seems that there is no relation among the entries of the matrix, and so if p divides n, then this is not an isomorphism. Many of the entries are 0.
Just about it.
Thanks. But if p does not divide n, then all the entries are in fact algebraically independent. So the regulator is indeed an isomorphism. So this is maybe the most sweetest way I prove that the determinant was not 0. Thank you very much.
Questions? When you said valence conjecture, what were you talking about? Like, you think of this Hodge-Pink thing as an analog
of classical Hodge structures, and there is, the regulator map is of Bayesian is defined in that way. So you take an extension of mixed modulus, and you apply the Hodgerization given here, and the Bayesian conjecture predict that when the weights are small enough, then this is an isomorphism, and the determinant in the well-chosen basis is the variance.
Running side as well.
Here, I mean, classically, that's just odd structures with an action of the complex conjugation. Ah, yes, that's yes, and that's maybe some cohomologies. Yes.
For Wolkischen algorithms, is such being realization is like the crystalline one?
Not crystalline. I guess you have you will have to compute along a side. I mean, this is already. Yeah, I'm not sure.
Zeta function, you can also make sense of it for t-motivic.
Ah, yeah. I forgot to mention the zeta function actually. So maybe that you just mentioned here that's we also computed this thing, which is 0 if I mean it's some kind of dual to the extension group. So they have now 0 if n is positive. There are 3 of rank 1 if q minus 1 does not divide n. And that's not working. That is not working. In fact, the torsion, so we were not able to precisely compute the torsion, that is the feeding ideal. This is precisely generated by the zeta function. Okay. So now, so as I explained, for negative values of n, the zeta value is a polynomial, in fact. So, and I mean the first non-zero coefficient. So this is computed with the zeta value. And yes, you can make sense of the zeta value of any t-motivic.